Kia ora. This is another one of the questions from this year's Level 3 Differentiation School exam. So this is a merit question, but it had just one thing in it that I thought was quite nice if you are sitting A-level. So I'm going to do this question the way that you would usually do it in Level 3 Calc, and then I wanted to show students who are doing A-level how you can do it using what we know about differentiating the inverse tan function as well, although that wouldn't be how I would do it. But it's quite cool to see the two things linking up. Okay, so we've got a right angle triangle A, B and C, and AC has got a fixed length of 9.5 centimetres, and AB, which is this side here, is increasing. So straight away, I know that that's going to be in the question, so I'm just going to give that a label, and I called that X. So if side AB is increasing at a rate of 3 centimetres per second, find the rate theta is increasing when the length of AB is 7 centimetres. Sorry. Yeah, when the length of AB is 7 centimetres. So what's going to happen here is that this side length is going to stay the same and this angle is going to change. So if we start out like this, if this is theta and this side length is getting longer and this is 9.5, then as this side here, x, gets longer, then if that side stays at 9.5, well, that's a terrible triangle, you can see that theta is actually getting smaller, right? So the answer that we get here should be a negative number because, again, this side is not changing, this side is growing. And what we need to do is to figure out what the rate of change is in the angle when that length is 7 centimetres. So I've said this in class before, but probably the biggest mistake that we see in these questions is when students immediately try to use that 7 centimetres figure, and we want to use that right at the end of the problem. So what I have to find here is d theta by dt when x is equal to 7. We're going to set a chain rule relationship up for that. We're given dx by dt Sorry guys, I just have to turn off ink to shape. So dx by dt is equal to 3 centimetres per second. So we're going to use this to set up something with the chain rule. So d theta by dt is going to be something times something. We've got dx by dt. So if we have d theta by dx here, then we're done. Now let's have a look at what theta is. Well, we've got x in here. So we can write that tan of theta is equal to 9.5 over x, opposite over adjacent. The problem with looking at this straight away is that then we have to do theta is equal to tan inverse of 9.5 over x. Now, as I said at the very start of this, if you're doing A-level, then we do know how to differentiate that function, but it's kind of a messy way to do this problem. A nicer way to do it is to say, well, what have we got here? We've got x here. So we've got a link between x and tan theta. So we can get dx by d theta. And once we've got dx by d theta, we know that we can go from there to get d theta by dx, because this will just be the reciprocal of this thing here, right? They're not equal, but they're closely related. So that was how I did this problem first up. As I just wrote down, what have we got here? Well, we've got tan theta is equal to 9.5 over x. X is equal to 9.5 over tan theta, which is 9.5 cot of theta. Sorry, that should say, that's right. Now, dx by d theta is equal to negative 9.5 cosec squared theta, which is negative 9.5 over sine squared theta. And that means that d theta by dx is equal to negative sine squared theta over 9.5. So we're just about there, right? Because all we've got to do here is link those two things. So d theta by dt will be negative, I'll do it slowly, negative 1 over 9.5 times sine squared of theta times 3. So the last thing we've got to do is to say that we're being asked to evaluate that derivative when x is equal to 7. So that's a very, very badly drawn triangle. That's so not to scale that I just have got to delete that. Okay, let's try again. So 7 is lower than 9.5. So it looks more like this. So here's 7, 9.5, and now we're figuring out what theta is. So theta is the angle whose tan is 9.5 over 7, and that works out to be 0.93577 radians, or I don't know what that is, it's probably 50 something degrees. So chucking all of that in together, we get this. We get d theta by dt is equal to negative 1.1 over 9.5 times sine squared of that. There's nothing fun about these numbers, so I didn't bother to write all the values out, but I ended up with negative 0.20467, and that's the units would be radians per, I guess we're dealing with seconds. Just have to check from the question if it was seconds or minutes. Yeah, seconds. Okay, so that's the first way to do it. So if you're doing level 3, don't worry about watching the next bit. If you're doing A level, I think it's probably worth a little bit of revision on differentiating the inverse tan function. So in this question, we've got theta is equal to tan inverse of 9.5 over x. So we can get dx by d theta directly. Sorry, not dx by d theta by dx directly, using the chain rule. So it's going to be 1 over 1 plus this squared times the derivative of this, right? So this is the inside function, and this is the outside function. So writing that out slightly differently, we can write this as 9.5x to the negative 1. So d theta by dx will be 1 over 1 plus this squared, and the derivative of that inside function is negative 9.5 over x squared. Okay. So you can see that I don't think there's any benefit really in doing it this way. I think the numbers are actually messier, but now I can substitute in without ever working out what theta is. So at x equals 7, we get d theta by dt is going to equal 1 over 1 plus 9.5 over 7 squared times negative 9.5 over 49 times dx by dt, which is simply 3. And when we bung all of that in, we not surprisingly get the same answer. So we get negative 0.20467. Okay, thanks for watching. People in 13 MCA, curious about whether you like doing it with that inverse tan thing. In the exam, I think only one of you attempted that method, and although he did a good job with it, I'm pretty sure that he mucked up the derivative of the inside function bit here. And I do think that's worth going over because this can come up in A-level papers. It's just not a good way to do this particular question.